Okay. So our first test is scheduled for next Tuesday, right? Does that sound right? Okay. So exam one is, I think it's Monday for the night class. That would be the 16th. And Tuesday, 9/17 for the day class. If you can't make it to the day class for the test, but you can make it the night before, feel free to do that. You're always allowed to do that if that works out. The topics are going to be just everything up through the stuff that I've assigned so far. So it's going to be related to the problems that you've done so far, which I know isn't very many yet, up through numbers 2 and 3 on one-dimensional particle kinematics. So this test is on a very small amount of material, but that just means you can, it should be a lot easier to sort of focus on what you need to make sense out of, and hopefully the scores will be really high. Yes. That's right. So it's only going to be on the stuff we've already done, basically. And numbers 2 and 3 are the ones with the house and the raft and the buoy, or going back and forth and drawing position versus time graphs. So you need to make sure you're comfortable with that kind of stuff. Does anybody have any questions about any of the assignment that I gave last time? Yeah.
So I was going through practice problem number 2, and it said something about average velocity and average speed.
Oh, okay.
Speed, I haven't noticed it.
Right, we haven't done that yet.
We haven't done that? Okay.
Yeah. So average, I guess we talked about average velocity at the end of last time. I'm sort of getting away from asking those questions recently, so I guess that's why I haven't talked about it. I think it's fair to say that stuff won't be on the test. But here's the average velocity is the position at the later instant minus the position at the earlier instant. Divided by the later time minus the earlier time. Average speed is the distance traveled divided by the elapsed time, so divided by the later time minus the earlier time. One interesting thing about the average velocity calculation is notice that if your later position is the same as your earlier position, no matter how fast you've been moving to get there, if you end up back where you started, your average velocity is always 0. So like if you're talking about the average velocity for someone running around a track or something, no matter how fast or slow they go, the average velocity is 0. The average speed is obviously something and is different for everybody. But I'm not planning to ask those questions on the test. Any other questions about the homework assignment? Well, we might as well spend a little time today let's do one problem like that. So I'm going to just make up a problem and give you some time to work on it, and then I'll go through it to make sure that you're thinking about it the right way. So let's say that's a cliff, and this is a bungee jumper. Okay, and let's say that how far do you go in bungee jumping? Let's say that you go 60 feet. Is that too far? Let's say that this distance is 30 feet. And let's say this distance is, might as well say something different, 20 feet. And then the water and rocks and sharks are below there. That bungee, by the way, is way too long for that jump. Okay, that's better. So let's say that the person jumps. I'm going to name these 2 points. So let's call this point A, B, and C. I didn't plan this out very well. Okay, so anyways, he's going to end up, there's no sharks or rocks, let's say. He's going to end up in the water. You get wet on this ride. Okay, so the person jumps, hits the height B at 1 second. Hits C 0.5 seconds later. Hits B 1 second later. And hits C again 1 second later. And then the ride's over, you're just hanging in the water. And we want to graph the position, draw the position versus time graph. And first we're going to do it with the 0 position at the water, at C, and the positive direction up. And 0 time at the instant of the jump. Okay, so take a few minutes and see if you can think through this problem. And after everybody's had enough time to work on it, I'm going to go through it, and you can compare your work to the way I do it. Make sure that you're thinking about this the right way. And then we'll do a part B too, where we make different choices about 0 position and stuff. And then after we're done with this, we'll go on to new material. Okay, so go ahead. All right, so I'm going to set this up sort of the same way that I have before. So this is the point A, this is the point B, and this is the point C. And the motion starts here Then we know something when the person gets there, something when the person gets here, something when the person gets here, and then back, right? I think we know all these times. And the distances are 30 feet, and the distance between those two is 20 feet. And it takes 1 second to cover the distance from A to B, then half a second to go from B to C, and then 1 second to go from C back to B, and then 1 second to go from B to C. And none of this stuff is affected by the choices of zero position, positive direction. These are just describing what happened. Okay. So now we're going to choose the zero position, the positive direction. So the zero position that we chose was at C. So there's 0. And we chose the positive direction to be up. And now based on that, we can label these other 2 points. If you start at 0 and go 20 feet in the positive direction, what's the position you're at? Yep. And if you start at 20, positive 20, and go another 30 feet in the positive direction, what's the position? 50, yep. And the 0 time was when the person jumped, so that means that this is at 0 time. If you wait 1 second after 0 time, you're at 1 second. If you wait half a second after 1 second, you're at 1.5. 1 second after 1.5, you're at 2.5. And 1 second after 2.5, you're at 3.5. Any questions about those? And now to write it in a little table, our first instant, we're at 0 time, 0 seconds, and we're at position positive 50. The units are feet. The second instant is at 1 second, and the position is 20 feet. The third instant is 1.5 seconds, and we're at position 0. Then the fourth one is at time 2.5 seconds and position 20. And then the last one is 3.5 seconds and position 0. And then we're just plotting that. The y-axis is position, the x-axis is time. The times that matter are 1 second, 1.5 seconds, 2.5, 3.5. And the positions are 0, 20 feet, and 30 feet. 30 more feet. So 0, 20 feet, and 50 feet. So we start at the point 050. Then at 1 second, we're at position 20. 1.5 seconds, we're at 0. 2.5, we're at 20. And 3.5, we're back at 0. So it looks something like that. Any questions about that? Okay, let's do one more. Maybe that's sort of overkill, but this is the hardest thing that's going to be on the first test. So let's just do one more. So part B, we're going to use the same motion. I mean, I pretty much do that on all of these kind of questions. So let's say that the 0 position is at B. The positive direction is down. And 0 time is 1 second before the person jumps. Okay. So see if you can go through that again with those choices. So I'm going to start out. So that's what I drew last time. And I'm going to get all this stuff that's specific to last time out of here. Okay, so this is all the stuff, again, that doesn't depend on our choices of positive direction, 0 position, that kind of stuff. No matter what you choose, the person goes down the first 30 feet in 1 second, goes down the next 20 feet in half a second, and so on. Okay, and this time we're choosing the point B to be the 0 position, and the positive direction is down, so the negative direction is up. And if you start at 0 and go 20 feet in the positive direction, then this has to be positive 20. And if you start at 0 and go 30 feet in the negative direction, then this has to be negative 30. And this time we start the stopwatch a second before the person jumps. So that means that at the time the person jumps, the stopwatch says 1 second. 1 second later, the stopwatch says 2 seconds. Half a second later, it says 2.5. 1 second after that, it says 3.5. And then 1 second after that, it says 4.5. And so at the first instant, we're at time 1 second and position negative 30 feet. At the second instant, we're at 2 seconds and position 0. At the third instant, we're at 2.5 seconds and position positive 20 feet. At the next one, we're at 3.5 seconds and 0. And then the last one is 4.5 seconds and position 20 again. So for this graph, the times that matter are 1 second, 2 seconds, 2.5 seconds, 3.5, and 4.5. And the positions that matter are 0, positive 20, and negative 30. And now plot these 5 points. At 1 second, we're at negative 30. At 2 seconds, we're at 0. At 2.5 seconds, we're at 20. At 3.5 seconds, we're at 0. And then at 4.5 seconds, we're back at 20. And so the graph looks like this. Yes? Why would what? That first, okay, because, so the way that you need to think about it is, it says what your zero position is, okay, and our zero position was B. And then it says what your positive direction is. It said down. That means anything up from 0 is negative. Okay. And then just go, so start at 0 and just count in the two directions. We're starting at 0 and going 20 feet in the positive, so this is labeled positive 20. And we're starting at 0 and going 30 feet in the negative, so that has to be negative 30. And then the motion started here at the cliff. And so just look across and you're at negative 30. Yes?
Do you not plot the position at 0 seconds?
You could. It doesn't matter to me. So it would just, I guess it would just look, we don't exactly know what happened. As far as we know, like he parachuted in at exactly this instant or whatever. But I mean, that I wouldn't take off points for that or anything. Any other questions? Yes. It said positive facing down, or it should have. Positive is facing down, so anything up is negative. Is positive. Oh, that's how I have it. Yeah. So it starts out at so once you have this drawn out, it's really just at each step just reading the old graph. You know, we said this was 0. That was our choice. You know, the given to us. Positive is down. That means this is negative, and that lets us label these two. And then, so we start out at negative 30, go down to 0, go down to 20. Now we're just taking the time and the position at each of these instants to get there. And then we're just plotting those points. That's right. I mean, you could switch what they're called if you wanted, but what you can't change is that the person starts at the top of the cliff, 1 second later goes to the middle level, half a second later goes to the water, and so on. You can't change like physically what the person does. Any other questions? Yes. Yeah, so if, exactly, if the 0 position was C and positive was down, then this would be 0 and then 20 feet in the negative direction, so this would be negative 20. And then negative 20 and another 30 feet in the negative direction, this would be negative 50. Any other questions? Well, on Thursday, if you have any questions related to the test, feel free to bring them and I'll go through problems or whatever in class. But for the rest of class today, I'm going to go through stuff that isn't relevant for the test. Just keep going on new material. So last time, we started talking about velocity. And remember, I said there are two types of velocity. Average velocity And to do that, you have to choose two instants. I wrote it before as T1 and T2. I'm going to write it now as T early and T late. But an earlier instant and a later instant. And then the second one that we haven't gotten to yet is instantaneous velocity. And instantaneous velocity is at a single instant. So for this one, you're only going to choose one time to define it. Okay. So for average velocity, you have to choose two of them. For instantaneous, you only choose one. This one is going to be important to us. Average velocity is not going to be very useful to us at all as this class goes on, but I had to give the definition of that one so I can sort of explain what instantaneous velocity is. But we did see that average velocity, the way you calculate that is you take the position at the later instant, you subtract the position at the earlier instant, and then you divide the elapsed time, which is t at the later instant minus t at the earlier instant. And I showed you the case of position is equal to time cubed. I just, made up a function. And it looks something like this, the position versus time graph that we looked at. And then I showed that the meaning of the average velocity is the slope of the line between those two chosen instants on the graph. Okay, so what does instantaneous velocity mean? So now we'll define instantaneous velocity. And the way that you calculate instantaneous velocity, the meaning of it, is you choose the point where you want the instantaneous velocity. And then you choose 2 points, one on each side of that t that you want, and calculate the average velocity. And then you choose 2 points a little closer on each side and calculate average velocity. And then 2 points a little closer, and you keep pinching in your 2 points closer and closer to the point you care about. And what you see is that eventually they start to head towards, in some cases, it'll take 3 times doing it. In some cases, it would take 1,000,000 times doing it. But eventually, you'll start to get closer and closer to a value. That idea is called limits. And in the limit, as your 2 outside points get closer and closer to the one you want, that limit that you're heading towards is called the instantaneous velocity. And so here's what it looks like. If we have our position as a function of time equal to time cubed again, then the velocity, instantaneous velocity, is the slope of the tangent line at the chosen point, that chosen instant t. Okay, so if this is the position versus time graph, Oh yeah. And this is time equals 1 second. Then the tangent line is this at that point. And the slope of that tangent line is the instantaneous velocity. So this is the tangent line. And the instantaneous velocity is the slope. And in this case, it has a value of 3, right? Yes. Obviously, like to calculate instantaneous velocity, I said like in some cases, if you did it using that limit idea, you would get your answer pretty fast. In some cases, it would take a million times. Well, that's not good if you're trying to calculate an instantaneous velocity and it takes you a million times to, calculations to calculate it. You got better stuff to do than that. And so that's what calculus is about, is calculating limits. And once you start doing calculus 1, you see that it's very quick and simple to calculate the slope of that line. Yes? Yeah. Okay, so I didn't write anything down, but I said the idea of calculating the slope of that tangent line there is first take a point on either side of the point that you care about and calculate the average velocity. Okay, you might get like 6 or something. And then calculate average velocity for 2 points that are a little closer to the one you want. And you might get 4. And now calculate the average velocity for 2 points a little closer. You might get 3.3. And little by little, as you calculate an average velocity of 2 points that are closer and closer to the one that you care about, that average velocity is getting closer and closer to that value 3. So that's how it works. In the limit, as you keep taking these average velocities closer and closer to the point you care about, your average velocities get closer and closer to 3, which is the true value. Yes?
So is the average velocity and the instantaneous velocity parallel?
No, not necessarily, because the average velocity is defined by 2 instants, and the instantaneous velocity is defined by 1. So you can change that slope depending on what your 2 points are. You know what I mean? What we really care about is the instantaneous velocity, and your speedometer gives you a value of the instantaneous speed. It doesn't tell you your average speed over the last hour. It tells you right at that instant, right now, how fast are you going, and we want the velocity equivalent of that. Yes. Yeah. Yeah. So for the average velocity, you need to choose those times t early and t late, and the corresponding positions at those times t early and t late to calculate it. Any other questions right now? Okay, so here are some things about instantaneous velocity. So notice, these are important to remember. The absolute value of instantaneous velocity is instantaneous speed. Okay, so those are really closely related. The only difference is the instantaneous velocity can be plus or minus. Instantaneous speed can only be positive. And so what does the sign mean on the instantaneous velocity? The sign of the instantaneous velocity is the direction that the thing is moving at that instant. So if you have an instantaneous velocity of negative 50 meters per second, that means that the thing is moving with a speed of 50 meters per second in the negative direction. If you have a positive 50 meters per second, it means it's moving with a speed of 50 meters per second in the positive direction. That's what the sign means. And the last thing I want you to keep in mind is since instantaneous velocity is more important to us than average velocity, since instantaneous velocity is more important than average velocity, if you ever see something just talking about velocity and it doesn't specify which one, it means instantaneous velocity. Anytime you have a question that does want the average velocity, we'll specify that. Okay, so notice that I haven't given you a way to calculate the instantaneous velocity yet. The way we would do that is with calculus. We have to come up with other formulas. We can't just go to like the definition of instantaneous velocity. We'll have to come up with other formulas for calculating it in specific cases. And then the last thing that we have to define, so now we've defined position and velocity, and now we have to define acceleration. And to understand what acceleration is, think about it this way. Just like velocity measures changes in position, acceleration measures changes in velocity. And because of that, the formula, the definition of acceleration looks pretty similar to the definition of average velocity. It's just we put velocity in place where position was before. So acceleration is equal to the velocity at instant 2, or let me write that again as the later velocity, minus the earlier velocity, divided by the later time minus the earlier time. And there are a couple of things that I want you to notice about acceleration. The first one is, for us, I mean, just like we defined average velocity and instantaneous velocity, you could define average and instantaneous acceleration. We won't have to worry about that because we'll always have constant acceleration, acceleration that doesn't change. We'll always have constant acceleration. And so what that means is the average acceleration is equal to the instantaneous acceleration. And we're just going to call it the acceleration. The second thing I want you to remember about acceleration is A equals 0 is exactly equivalent to constant velocity. So if the velocity isn't changing, the acceleration is 0. You can think of those as two different ways of saying the exact same thing. Either the acceleration is 0 or the velocity is constant. Okay, so now what about speeding up and slowing down? We're dealing with this in lab this week, so a few people have already seen this a little bit. And if I asked you to guess, I think most people tend to say that a positive acceleration probably would mean that the velocity, that the thing is speeding up, and a negative acceleration means the thing is slowing down. But it's more complicated than that. Speeding up and slowing down has to do with the signs of both the velocity and the acceleration. Okay, you can't tell whether something's speeding up or slowing down without knowing both of those. So if velocity and acceleration have the same sign, then the object is speeding up. And if velocity and acceleration have opposite signs, then the object is slowing down. And what about the units for acceleration? Well, units of acceleration are always length divided by time squared. And so if you're in SI units, like we are most of the time, SI units for acceleration are meters per second squared. Okay, so let's see how this works with, so let's say that we have a car that's speeding up. Oh yeah, sorry. Mhm. Sure. Okay, so this car is speeding up. And let's think about how the signs of the uh, velocity and acceleration work with this, okay? So what would happen if we chose our positive direction to be this way, first of all? Okay. Do we have enough information to know what the sign of the velocity is of that car? We do. Yeah, so the sign of the velocity is the direction the thing is moving. So the velocity is positive. Okay. And that's right. We know that it's speeding up. So we know that the acceleration has to be positive. And you can think of these as, these signs are also just directions. So you can think of it as arrows pointing in the directions of these things. So a positive velocity means the velocity is this way. Okay. The positive, acceleration is positive and positive is to the right. So the acceleration also has to be this way. Okay. So now let's think about what would happen if we chose the positive direction to be the other way. Now what's the sign of the velocity? Negative. It's speeding up, so what's the sign of the acceleration? It's speeding up, so they have to be the same sign. So if velocity is negative, acceleration also has to be negative. And now think about those arrows again. This is the thing that can't change. Like the velocity and acceleration have to, this thing is, it doesn't know anything about our math. So what we want is when we change the signs for the arrows to still be in the same direction. Does it work that way? You know what I'm asking? Does that make sense? So now our positive is going this way because we just chose that, that's our choice. But based on the positive going this way, the car is moving in the negative direction. Okay. And negative is that way. And it's speeding up. So up, that should say acceleration. So the acceleration has the same sign as the velocity. Okay. So it has to be negative, and negative acceleration means that way. So no matter which way you choose your positive and your negative directions, what you get out of this example is a velocity pointed that direction and an acceleration pointed that direction. The signs only have to do with the directions. The how fast you're going and how quickly you're slowing down or speeding up, that's the magnitude of the velocity and acceleration. Okay, so now we're finally about to get into the equations that we can use to calculate acceleration and velocity and stuff. So these are the equations for 1D particle kinematics with constant acceleration. Okay, so what I'm going to call PI and VI are the position and velocity when time is equal to 0. And PF and VF are the position and velocity when time is equal to time final. Then we have these three equations. Velocity final is equal to velocity initial plus acceleration times time final. Position final is equal to position initial plus velocity initial times time final plus 1/2 times the acceleration times time final squared. And the last one says 2 times the acceleration times the quantity P final minus P initial is equal to V final squared minus V initial squared. Okay, so I'm going to do a quick example to show sort of how the variables and stuff fit together with these equations. And then at the start of next time, I'll give a detailed step-by-step process for how to use these equations. And you can just follow the steps until you're sort of comfortable with it. Okay, so let's say that a car that's traveling 20 meters per second hits the brakes and stops in 2 seconds. What's the car's acceleration? Okay, so the car starts out traveling to the right, hits the brakes. It takes 20 meters, so at this place here, the car is stopped. So this is 20 meters. And we want to calculate the acceleration. And like always, we're going to choose a 0 position, a positive direction, and a 0 time. Now we're going to have to choose a final time too. So our 0 position is going to be where the car is when it hits the brakes. Our positive direction, might as well make that the direction of motion, but like before, you could do it either direction. Our time equals 0 is when the car hits the brakes, the instant the car hits the brakes. And our time final is when the car stops, the instant that the car stops. Okay, well, what do we know based on all these? At time equals 0, do we know the car's velocity? Yes, we know that the speed is 20 meters per second, and we know it's going in the positive direction. Wait, did I ask for position or velocity? Or what did I just, okay. So here's the stuff we know. Do we know the position of the car when time is equal to 0? Yeah, so PI is equal to 0. The velocity at time equals 0 is positive 20 meters per second. Do we know the velocity at time final? 0, because that's when it stops. So V final is 0. Do we know what the stopwatch says at time final? And so now we can use the first of these 3 equations to calculate acceleration. I'm going to use the one that says V final is equal to V initial plus A times time final. It says 0 is equal to positive 20 plus A times 2. And so A is equal to, I'll do it in steps. So negative 20 is equal to 2A. And so A is equal to negative 10 meters per second squared. And that's the answer. Does it make sense that the acceleration is negative in this case? How can you make sense out of that? Yeah, it's slowing down and the car is moving in the positive direction. So if something's slowing down, velocity and acceleration have to have opposite signs, and that's what we have here. Any questions about that? Okay, so next time on Thursday, I'll answer any questions you have about stuff related to the test, and then I'll get into a set of steps for using these equations.